Okay, so we're going to talk a little bit more about sampling today. Now, when we think about sampling, we usually have a population, and we're sampling from that population, and we compute numerical summaries of the samples. Numerical summaries from the samples are statistics, and the most common statistic that is calculated would be our sample mean, or X bar. Now, normally we wouldn't just sample once. If we really want to get a true view of what's going on, we're going to have lots and lots and lots of samples. Now, each sample probably is going to have a different mean. So this one could be different from this one's different from that one. Some of them might be the same, but more often than not, they're going to be different values. Now, because this varies, that would be a random variable. So for each value of a random variable, we can compute a probability. Now, the probability distribution of X bar, our sample mean, is called the sampling distribution. Now, here's an example of a sampling distribution. So say we have a tetrahedral dice. That's a pyramid with 4 faces. Each face is 1, 2, 3, and 4. Now, tossing the dice like sampling a value from the population 1, 2, 3, 4. Now, if we do it empirically, just what would be the mean, it should be 2.5 with a standard deviation of 1.118 if we're using our true means, because if we added those together, that'd be 10 divided by 4, 2.5, so forth. Now, suppose that we take that die and we toss it 3 times. 1, 2, 3, 1, 2, 3, 1, 2, 3. And the sequence of those 3 numbers is observed and maybe thought of as a sample of size 3 drawn with replacement. And we get all of these different samples. Now, each of those samples would have a mean. Each sample has a mean. And notice that every sample has a different mean. Well, if we took all of those means and found the mean of the means, it actually comes out to be 2.5. So notice this is the population mean of the sample mean is 2.5. Well, that's what we thought it should be. Now, our standard deviation actually comes out different. It's 0.6455. So that is different than what we would get statistically. So let's talk about how we could find that. So the first thing we noticed was the mean of the sampling distribution is the same as the mean of the population. That's awesome that it came out that way. Because if you take a whole bunch of samples, you get closer to your true population mean. But the standard deviation of the sampling distribution is, sorry about that, is less than the true population standard deviation. So when we're talking about the sampling distribution, the formula, which doesn't come easily, is actually that we take our population standard deviation and divide by the square root of the sample size. So here's our formula for the standard deviation of a sampling distribution. Now notice this is a sampling distribution. This means we have a whole bunch of samples that we've taken. Okay. Among students at a certain college, the mean number of hours of television watched per week is 10.5. That's from the population. And the standard deviation is 3.6. That's from the population. A simple random sample of 16 students is chosen for a study of viewing habits. Let X bar be the mean number of hours of TV watched by the sample students. And we want to find the mean and standard deviation of our sampling distribution. So not from the population, but out of all of the samples. Well, the mean is actually going to be super easy. Our mean of the means is going to be equal to the population mean. It's 10.5. Awesome. The standard deviation of the means is going to be found by taking the standard deviation from the population divided by the square root of the sample size. So we were given the standard deviation of the population divided by the square root of the sample size. The sample size was 16 students. So we will have 3.6 divided by the square root of 16. And that gives me 0.9. Pretty easy to find. Consider again that tetrahedral die. The sampling distribution of X bar can be determined from the table of all the means. Now, the probability that the sample mean is 1 would be 1 out of 64 because there's 64 possible samples. Only one has a sample mean equal to 1. Similarly, the probability of having 1.33 would be 3 out of 64 because that occurs 3 times, and so forth. So we can end up getting a probability distribution of our sample means, of all of those means. We could also look at that as a histogram. Now, the probability of just rolling a die, it's equal, right? 1 out of 4, 1 out of 4, 1 out of 4. But if I do that, a sample of 3 rolls over and over and over and over and over and over and over, I end up getting a histogram that looks like this. Now, this is a histogram of all of my samples, all 64 possible samples I could have. And notice, what shape does that make? Well, that's a symmetric shape. It's normally distributed. That's really cool to know, because then we can do stuff like we did with a normal curve. Now, not from just one sample, but from a sampling distribution, I can. Now, what if the population itself is skewed? Like we had one that was pretty even. But what if we have a population that's skewed? A larger sample size is necessary for us to get to be normal. Let's see what we mean. If we have a sample size of just 3, it's still skewed. Sample size of 10, it's still skewed. But if I get up to 30, look how pretty that gets. So the size of the sample needed to obtain approximate normality depends mostly on the skewness. But normally, 30 is large enough. The remarkable fact that the sampling distribution of our mean is approximately normal for a large sample is part of one of the most used theorems in statistics, called the central limit theorem. So the central limit theorem states that if n is greater than 30, if we have a sample with n greater than 30 from a population with mean mu and standard deviation sigma, then the mean of our means is the mean, And the standard deviation of our means is equal to the population standard deviation divided by the square root of n. Now, this applies for all populations. So if you know the population is sample from the population is bigger than 30, we can use these formulas. But if we already know that the population is symmetrical, like they say it's coming from a normal population, then we can have a smaller sample size. So if it already says it's normal, we don't have to worry about the sample size. But if they don't tell us that it's from a normally distributed population, our sample size has to be greater than 30. All right, so let's use those ideas to find some probabilities. A sample of size 45, check, that's bigger than 30, will be drawn from a population with mean 15 and a standard deviation of 3.5. Is it appropriate to use the normal distribution to find probabilities for our mean? Yes. Why? N is greater than 30. A sample of size 8 will be drawn from a normal population with mean -60 and a standard deviation of 5. Is it appropriate to use the normal distribution for our means? Yes. The population is normal. So remember, if the population is normal, the sample size doesn't matter. So if they state that that's normal, we can use our normal distribution. A sample size of 24 will be drawn from a population with mean 35 and standard deviation of 1.2. Is it appropriate to use the normal distribution, normal curve, to find probabilities of the mean? No. N is less than 30, and we don't know if the population is normally distributed. How would I know? Well, if I saw a histogram of the population, I could tell if it was skewed or normally distributed, skewed or symmetrical, but I don't see it, so I can't know that. All right, let's check these. Recent data from the US Census indicates the mean age of college students is 25 years and a standard deviation of 9.5 years. A simple random sample of 125 students is drawn. Can we use the normal curve to find a probability? Yes. And we're finding the probability that a sample mean age, so we're finding the probability that the mean is greater than 26. So we are able to use our normal curve. The mean of our means is equal to the population mean, so that's going to be 25. Our standard deviation, we have to take the population standard deviation and divide by the square root of the sample size. So the population standard deviation was 9.5, and I'm going to divide that by the square root of 125. So 9.5 divided by the square root of 125. I get 0.8497. It's best to go as many decimal places as you can. 4 is pretty good. So now I'm going to go to my NumWorks app. And I'm going to go to my normal distribution. And the mean we're going to use is the mean of the means. And the standard deviation we're going to use is not the population one, but the one for the means for my samples. And then we want to know when we're greater than 26, greater than 26, and that's 0.1196. and I'm going to probably mispronounce this, Hereford cattle are one of the most popular breeds of cattle. Based on the data from the Cattle Society, the mean weight of a 1-year-old bull is 1135 pounds with a standard deviation 97. This is coming from the population. Mean of the population is 1135, and standard deviation from the population is 97. Would it be unusual for the mean weight of 100 head of cattle, so N is 100, would it be unusual for the weight to be less than 1,100 pounds, for the mean weight? So we're finding the probability that the mean weight is less than 1,100 pounds. So we're finding the probability that the mean weight, the average weight from that sample is 1,100 pounds. Now remember, we're finding the mean of the means. Well, that's going to be 1135. The standard deviation of the means. We take the standard deviation from the population divided by the square root of n. So that's going to be 97 divided by the square root of 100. That's going to be 9.7. So now I'm going to go back. And the mean we're going to use is the mean of the means. So 1135. And the standard deviation we're going to use is this one we just found, 9.7. And we want to know when we were less than 1,100. Now notice that gave me 1.54, and it has this E negative 4. What that means is that means we've got, so 1.54 E negative 4 means times 10 to the negative 4. That means I have 0.000154. Is this an unusual occurrence? Well, remember, unusual is less than 0.05. So is this unusual? Yes, it is unusual.